Hello, dear listener, and for today's episode, we're going to be going on a few topics in the airframe and powerplant mechanics. Those topics are general, theory of flight, aerodynamics, the atmosphere, pressure, density, humidity, Bernoulli's principle and subsonic flow, and finally, motion. General. This chapter includes both assembly and rigging since the subjects are directly related. Assembly involves putting together the component sections of the aircraft, such as wing sections, empennage units, nacelles, and landing gear. Rigging is the final adjustment and alignment of the various component sections to provide the proper aerodynamic reaction. Two important considerations in all assembly and rigging operations are 1. Proper operation of the component in regard to its aerodynamic and mechanical function, and 2. Maintaining the aircraft's structural integrity by the correct use of materials, hardware, and safetying devices. Improper assembly and rigging may result in certain members being subjected to loads greater than those for which they were designed. Assembly and rigging must be done in accordance with the requirements prescribed by the aircraft manufacturer. These procedures are usually detailed in the applicable maintenance or service manuals. The aircraft specification or type certificate data sheets also provide valuable information regarding control surface travel. The rigging of control systems varies with each type of aircraft. Therefore, it would be impracticable to define a precise procedure. However, certain principles apply in all situations, and these will be discussed in this chapter. It is essential that the aircraft manufacturer's instructions be followed when rigging an aircraft. Theory of flight. Numerous comprehensive texts have been written about the aerodynamics involved in the flight of an aircraft. It is unnecessary that a mechanic be totally versed on the subject. However, he must understand the relationships between the atmosphere, the aircraft, and the forces acting on it in flight. In order to make intelligent decisions affecting the flight safety of both airplanes and helicopters. Understanding why the aircraft is designed with a particular type of primary and secondary control system, and why the surfaces must be aerodynamically smooth, becomes essential when maintaining today's complex aircraft. Aerodynamics. Theory of flight deals with aerodynamics. The term aerodynamics is derived from the combination of two Greek words, aer, meaning air, and dyne, meaning force of power. Thus, when aero is joined with dynamics, we have aerodynamics, meaning the study of objects in motion through the air, and the forces that produce or change such motion. Aerodynamics is the science of the action of air of an object. It is further defined as that branch of dynamics which deals with the motion of air and other gases, with the forces acting upon an object in motion through the air, or with an object which is stationary in a current of air. In effect, aerodynamics is concerned with three distinct parts. These parts may be defined as the aircraft, the relative wind, and the atmosphere. The atmosphere. Before discussing the fundamentals of the theory of flight, there are several basic ideas that must be considered. An aircraft operates in the air. Therefore, the properties of air that affect aircraft control and performance must be understood. Air is a mixture of gases composed principally of nitrogen and oxygen. Since air is a combination of a fluid of gases, it follows the law of gases. Air is considered a fluid because it answers the definition of a fluid, namely, a substance which may be made to flow or change its shape by the application of moderate pressure. Air has weight, since something lighter than air, such as a balloon filled with helium, will rise in the air. Pressure. The deeper a diver goes beneath the surface of the ocean, the greater the pressure becomes on his body due to the weight of the water overhead. Since air also has weight, the greater the depth from the outer surface of the atmosphere, the greater the pressure. If a 1-inch square column of air extending from sea level to the top of the atmosphere could be weighed, it would be found to weigh about 14.7 pounds. Thus, atmospheric pressure at sea level is 14.7 pounds per square inch. However, pounds per square inch is rather a crude unit for the measurement of a light substance such as air. Therefore, atmospheric pressure is usually measured in terms of inches of mercury. The apparatus for measuring atmospheric pressure is shown in Figure 2.1. A glass tube 36-inch long, open at one end and closed at the other, is filled with mercury. The open end is sealed temporarily and then submerged into a small container partly filled with mercury, after which the end is unsealed. This allows the mercury in the tube to descend, leaving a vacuum at the top of the tube. Some of the mercury flows into the container while a portion of it remains in the tube. The weight of the atmosphere pressing on the mercury in the open container exactly balances the weight of the mercury in the tube, which has no atmospheric pressure pushing down on it due to the vacuum in the top of the tube. As the pressure of the surrounding air decreases or increases, the mercury column lowers or rises correspondingly. At sea level, the height of the mercury in the tube measures approximately 29.92 inches, although it varies slightly with atmospheric conditions. An important consideration is that atmospheric pressure varies with altitude. The higher an object rises above sea level, the lower the pressure. Various atmospheric conditions have a definite relation to flying. The effect of temperature, altitude, and density of the air on aircraft performance is discussed in the following paragraphs. Density. Density is a term that means weight per unit volume. Since air is a mixture of gases, it can be compressed. If the air in one container is under 1/2 as much pressure as the air in another identical container, the air under the great pressure weighs twice as much as that in the container under lower pressure. The air under greater pressure is twice as dense as that in the other container. For equal weights of air, that which is under the greater pressure occupies only half the volume of that under half the pressure. The density of gases is governed by the following rules. 1. Density varies in direct proportion with the pressure. 2. Density varies inversely with the temperature. Thus, air at high altitudes is less dense than air at low altitudes, and a mass of hot air is less dense than a mass of cool air. Changes in density affect the aerodynamic performance of aircraft. With the same horsepower, an aircraft can fly faster at a high altitude where the density is low than at a low altitude where the density is great. This is because air offers less resistance to the aircraft when it contains a smaller number of air particles per unit volume. Humidity. Humidity is the amount of water vapor in the air. The maximum amount of water vapor that air can hold varies with the temperature. The higher the temperature of the air, the more water vapor it can absorb. By itself, water vapor weighs approximately 5/8 as much as an equal amount of perfectly dry air. Therefore, when air contains water vapor, it is not as heavy as air containing no moisture. Assuming that the temperature and pressure remain the same, the density of the air varies inversely with the humidity. On damp days, the air density is less than on dry days. For this reason, an aircraft requires a longer runway for takeoff on damp days than it does on dry days. Bernoulli's principle and subsonic flow. Bernoulli's principle states that when a fluid, air, flowing through a tube reaches a constriction or narrowing of the tube, the speed of the fluid flowing through that constriction is increased and its pressure is decreased. The cambered, curved surface of an airfoil wing affects the airflow exactly as a constriction in a tube affects airflow. Diagram A of Figure 2.2 illustrates the effect of air passing through a constriction in a tube. In B, the air is flowing past a cambered surface, such as an airfoil, and the effect is similar to that of air passing through a restriction. As the air flows over the upper surface of an airfoil, its speed or velocity increases and its pressure decreases. An area of low pressure is thus formed. There is an area of greater pressure on the lower surface of the airfoil, and this greater pressure tends to move the wing upward. This difference in pressure between the upper and lower surfaces of the wing is called lift. 3/4 of the total lift of an airfoil is the result of the decrease in pressure over the upper surface. The impact of air on the undersurface of an airfoil produces the other 1/4 of the total lift. An aircraft in flight is acted upon by 4 forces: gravity, or weight, the force that pulls the aircraft toward the earth; lift, the force that pushes the aircraft upward; thrust, the force that moves the aircraft forward; and finally, drag, the force that exerts a braking action. Motion. Motion is the act or process of changing place or position. An object may be in motion with respect to one object and motionless with respect to another. For example, a person sitting quietly in an aircraft flying at 200 knots is at rest or motionless with respect to the aircraft. However, the person is in motion with respect to the air or the earth, the same as is the aircraft. Air has no force or power except pressure unless it is in motion. When it is moving, however, its force becomes apparent. A moving object in motionless air has a force exerted on it as a result of its own motion. It makes no difference in the effect, then, whether an object is moving with respect to the air or the air is moving with respect to the object. The flow of air around an object caused by the movement of either the air or the object, or both, is called the relative wind. Velocity and acceleration. The terms speed and velocity are often used interchangeably, but they do not mean the same. Speed is the rate of motion, and velocity is the rate of motion in a particular direction in relation to time. An aircraft starts from New York City and flies 10 hours at an average speed of 260 miles per hour. At the end of this time, the aircraft may be over the Atlantic Ocean, the Pacific Ocean, the Gulf of Mexico, or, if its flight were in a circular path, it may even be back over New York. If this same aircraft flew at a velocity of 260 miles per hour in a southwestern direction, it would arrive in Los Angeles in about 10 hours. Only the rate of motion is indicated in the first example and denotes the speed of the aircraft. In the last example, the particular direction is included with the rate of motion, thus denoting the velocity of the aircraft. Acceleration is defined as the rate of change of velocity. An aircraft increasing in velocity is an example of positive acceleration, while another aircraft reducing its velocity is an example of negative acceleration. Positive acceleration is often referred to as acceleration and negative acceleration as deceleration. Newton's law of motion. The fundamental laws governing the action of air about a wing are Newton's laws of motion. Newton's first law is normally referred to as the law of inertia. It simply means that a body at rest will not move unless force is applied to it. If it is moving at uniform speed in a straight line, force must be applied to increase or decrease that speed. Since air has mass, it is a body in the meaning of the law. When an aircraft is on the ground with its engines stopped, inertia keeps the aircraft at rest. An aircraft is moved from its state of rest by the thrust force created by the propeller, by the expanding exhaust gases, or both. When it is flying at uniform speed in a straight line, inertia tends to keep the aircraft moving. Some external force is required to change the aircraft from its path of flight. Newton's second law, that of force, also applies to objects. This law states that if a body moving with uniform speed is acted upon by an external force, the change of motion will be proportional to the amount of the force, and motion will take place in the direction in which the force acts. This law may be stated mathematically as follows: force equals mass times acceleration. If an aircraft is flying against a headwind, it is slowed down. If the wind is coming from either side of the aircraft's heading, the aircraft is pushed off course unless the pilot takes corrective action against the wind direction. Newton's third law is the law of action and reaction. This law states that for every action, force, there is an equal and opposite reaction, force. This law is well illustrated by the action of a swimmer's hand. He pushes the water forward and thereby propels himself forward. Since the water resists the action of his hands, when the force of lift on an aircraft's wing equals the force of gravity, the aircraft maintains level flight. The three laws of motion which have been discussed are closely related and apply to the theory of flight. In many cases, all three laws may be operating on an aircraft at the same time. Thank you very much for listening. This was the second part to Airframe and Powerplant mechanics. I hope you enjoyed it, and until next time.